electric dipoles. Now, why do we need to talk about electric dipoles? We are squarely in the magnetism unit. What is going on with electric dipoles? It seems kind of like out of thin air. Well, here's the thing. We have actually skipped over talking about this way back in the first 4 homeworks where we totally could have. And the reason I did was because there's this universality about dipole behaviors that makes it so that it's far more efficient to just talk about dipoles all at once. So I basically delayed talking about this until I could just kind of talk about electric and magnetic dipoles together and just kind of group them all together. Now, let me show you. Let's say I have an electric field, okay? Now, let me suppose that I have a dipole in in this situation. Let's say I have, I don't know, I have a plus charge here and I have a minus charge like this, okay? And of course for a dipole we know that they are equal and opposite charges, so they'll say they're both of magnitude q, so plus q and minus q. And I'll also need at some point down the road here that they are separated by some distance. I'll call that d. So I'll kind of think of them as kind of being tied together to each other at a separation of d. Now, if you want, you can think of that as just, you know, like a little magic metal rod or something that's holding them together. Of course, in reality, this is usually some sort of inside of the atom, there's forces holding it together. So electric forces that are holding them at a certain distance apart. So if we look at this, we know that positive charges feel a force with the electric field and negatives feel a force opposite. So the plus charge wants to go downstream, negative charge wants to go upstream. If you look at this, of course, these two forces are going to be equal and opposite, so the net force is 0. However, it is going to rotate until it is in a certain alignment, and as you can probably guess, that alignment looks like this. And so at that point, the positive charge feeling a force downstream, the negative charge feeling a force upstream. The forces will cancel out in all situations, but in this situation, the torque will also be 0. That is its happy place. And so what we're going to do is we're going to define an electric dipole vector. So electric dipole vector. And again, some people like to call it electric dipole moment. Okay? I use for this P vector. Here's how it's defined. I'll put the size here, I'll put the direction there. The direction of it is defined as that it points from minus to plus. Okay? So let me draw it in here. So points from minus to plus. Here, points from minus to plus. This is not to be confused with the field made by the dipoles. This is just a construct that we are using to define how this dipole is oriented in space. So again, if someone gives you this dipole vector and just tells you the arrow points like this, you know there's a plus on or minus on the tail end and a plus on the head end. Okay, that's the definition. Now, why would you define it that way? Well, if you're looking at this, you're going, the net torque is 0 when the dipoles align with the field. It's exactly the same deal, right? So we want to set up so that it's exactly analogous to everything we've already talked about. So if we're going to go here, the electric torque on this is going to be, the direction is going to be that the electric dipole experiences the torque that it wants to align with E external. Okay? So, just like before, the magnetic dipole wants to align with B external. Now our electric dipole wants to align with E external. Now, if you're wondering how we can have everything be so perfectly analogous. Of course, this is all perfectly by design. We're forcing it to be that way. We're sort of forcing there to be a universality between what the two different kinds of dipoles. So, so let's see, what do we have? So let's work out the formulas here so that we can fill in the gaps here. So I'll use this right here as my jumping off point. I'm going to write over this. Again, my torque formula, RF sine theta. So here's my center of mass right there. And my leverage that this force has, well, that's just half the length of the dipole, so d over 2. The force is electric, so that'll just be Q times E. And then the angle that I would use, I draw a dotted line out from the pivot through the force application point. Boom, there's my theta. And it's a good time to look at the fact that that angle, theta, is exactly the same. If I copy my electric field vector over here, it's exactly the same as the angle between my newly defined dipole vector and the field. Okay? And then, of course, I've got two of these forces, so get double the torque. Twos wipe each other out. And let's see what I get. There is my torque formula. The magnitude of the Q on each side, D, E, sine of theta. And at this point, I'm going to take this, and I'm just going to call it. This is going to be the magnitude of my dipole vector. Okay? So magnitude of my dipole vector is Q times D. So this is just, again, what is this electric dipole vector? It encapsulates all the properties of the dipole. We have a lot less properties here. All we have to really package in is how much charge is on either side. So Q on either side, the magnitude goes here. D, their separation. And then the direction, which points from minus Q to plus Q, tells us how that dipole is oriented in space. And then look at my formula. My formula comes out in exactly the same form as previously. The torque will be PE sine of theta between those two. And if that looks a heck of a lot the same as MB sine of theta, well, that's of course because we basically made that happen. So here we have the two dipole types, electric, magnetic, the type of fields they're affected by, electric field and magnetic field from outside, and the sine of the angle between them. So pretty much come up with the same equation, and if the torque formulas are the same, we don't need to redo the derivation. If this was the magnetic formula, then of course the electric formula will be just the same. So replace magnetic dipole with electric dipole, replace magnetic field with electric field. So there you have it. So we have discovered a kind of universality to dipole behavior, and let's take a look at what all the connections bring us to. Okay, so both of the formulas are in this form. Okay, I guess I should back this up. So the torque is going to be whatever the maximum torque is in the front times the sine of the angle between them, which of course can reduce the torque. So that looks like this. The torque will be torque, some maximum torque times sine of the theta between them. Okay, so sine, I've plotted the sine function here from 0 to 180. And of course it just goes up, comes back down. It's 0. There's 0 torque at 0 degrees and 180 degrees. And I've drawn that in here. The field direction is like this. And again, I'm trying to draw this universally so that this could be either the electric field for electric dipole or a magnetic field that's affecting a magnetic dipole. So, first of all, we know that dipoles like to align with fields. So that when this dipole, whether this be a magnetic dipole affected by a magnetic field or an electric dipole affected by an electric field, Dipoles like to align with the field. That's why they experience zero torque, and their potential energy is minimum. So this is going to be not only zero torque, but stably so. So that's my example A here. So going back here, example A, I have zero torque. And then over here, and label this C, this is when the dipole, again, regardless of the kind it is, it also experiences zero torque. Corresponding function returns to 0 at 180. But this is where the potential energy is maximum, and so that is where this is an unstable equilibrium. So that's orientation C. And then here, orientation B, at 90 degrees, when the dipole is 90 degrees to the field, the torque is maximum. So again, the torque is maximum, and again, perhaps misleadingly, the potential energy is 0, which is not the highest or the lowest. And then the maximum torque here is going to be, if it's a magnetic dipole, that's MB, and if it's an electric dipole, it will be PE. Going back down here, remember we said that the potential energy basically takes this form. Basically drawing it here, it looks like a negative cosine. So it's a cosine function that's flipped upside down. So at 0, 90, and 180, we can see that the minimum potential energy is right here. It is at 0 degrees. Minimum potential energy happens when the dipole aligns with the field. That's why they like this orientation. That's the lowest potential energy. And that's why it's stable. We get this weird 0 here, where it's not the highest or the lowest. That's orientation B. And then, of course, the reason why this anti-alignment, where the dipole points opposite to the field, is unstable is because that's the very maximum potential energy that you can have. So the system wants to go in this direction, towards the lowest value possible. And then this maximum value, again, right here, this is MB or PE, depending on the type of dipole you have. So there's some questions on this on the homework, and I think there's one that even sort of shows you these. It's definitely worth taking a look at and understanding this kind of universal dipole behavior. Take a look at these two graphs that try to purposely draw them so that they line up here. So this 0 and this 90 and this 180 line up, so you can see at each angle, 0, 90, and 180, what's the potential energy and what's the torque doing. And you know, some people just like to visualize it with the graphs, but conceptually, the big takeaways here are that no matter what kind of dipole you have, it likes to align with the field. So the dipoles like to align with the field. If they're not there, they'll experience torque until they are. That's because that's the lowest potential energy. The dipoles will get stuck if you get them perfectly stuck, anti-aligned or pointing opposite to the field, because that is a zero torque state. But it is unstable. The potential energy is maximum. If it gets any slight little breeze that knocks it, it'll go back down to this preferred orientation. And then we get this orientation here, we get maximum torque, and the potential energy is set 0 there. I think the pendulum analogy, if you really understand the pendulum analogy, then this will greatly help you. And I even showed you in the pendulum analogy why it might make sense to set the potential energy here, 0 here, for that as well. And I guess a final remark is, how is it possible that the electric dipole torquing never really came up? Well, the only real time where we had electric fields causing dipoles, here's an example. We had an electric field, and we had like a neutral conductor. Well, this was what we call an induced dipole. So it isn't there already, and we saw that it charge polarized like this. And I want to point out, if I draw the dipole vector from minus to plus, well, in that case, notice that the dipole is already in the preferred orientation, pointing with the field, so there was no torque to go along with this situation. Okay, so if the dipole already happens to be aligned with the field, then you don't need to worry about this. So this is not something that really you have to worry about for induced dipoles. This is only when you have an existing dipole already, and that dipole happens to be in a bad orientation, or quote-unquote bad orientation, then it will experience torque until it is aligned with the field. And before you marvel at how could this universality of dipole behavior be so incredibly the same, how could it be that if you have an electric dipole, how could it want to align with the field, and if you have a magnetic dipole, how does it also want to align with the field? Remember, this is all things that we made it be so by designing it, by defining the dipoles in the way that would make those behaviors similar. When we have a magnetic electric dipole, what we mean is that we have this, and the magnitude of this is Q times D. When we have this magnetic dipole, that actually signals we have a current loop in a completely different plane as this, and the magnitude of that dipole will be NIA. So essentially what we're doing is we're taking the big differences in the two situations and we're absorbing them into these constructs so that we can see a sort of similar universal behavior in dipoles by the way that we do the packaging.